We're going to take a look at 12, 13, and 14 on the uniform circular motion problem sheet. Number 12, a student whirls a yo-yo in a horizontal circle. That's like one over your head, like you're trying to throw a lasso. The yo-yo has a mass of 0.2 kilograms and is attached to a string that is 0.8 meters long. A, if the yo-yo makes a complete revolution every second, what force must the string exert on the yo-yo? And B, if the student speeds up the yo-yo to have it make a complete revolution every half a second, what is the force the string exerts on the yo-yo now? So for number 12, numbers that we were given, the mass is 0.2 kilograms, the radius is 0.8 meters, the time it takes to go around once is 1 second, the centripetal force is what I want to find. So what equation should I use? Well, I'm going to use the one that has time, the radius, and the mass, which is m 4 pi squared r over t squared. Mass is 0.2 kilograms, 4 pi squared, and the r is 0.8 meters, and the denominator is 1 second, and I've got to square that. When I plug my numbers in into my calculator, I get a centripetal force of 6.3 newtons, which is how much tension must be in the yo-yo string. Well, what if we double the speed and the time it takes to go around is 0.5 seconds? Well, my equation's exactly the same because the m hasn't changed, the r hasn't changed, and we're still using time. So I'm going to plug in my numbers again, which is 0.2 kilograms times 4 times pi squared times r, which is 0.8 meters. And now I'm dividing by a half a second squared instead of 1 second squared. And I get a centripetal force of 25.3 newtons, which is 4 times as much force since I'm going twice as fast. Now we'll take a look at number 13, which is a 60 kilogram skater is skating with a velocity of 18 meters per second, and they're going to a curve that has a radius of 20 meters. How much friction must be exerted between the skates and the ice to negotiate the curve? Now, I know we normally say that ice does not have friction, or at least not very much, but in this case, we're talking about ice skates, which are blades, which are designed to have very little friction going front and back, but do have some when you're trying to push off going left and right because they can cut into the ice a bit. So the mass of the skater was 60 kilograms, the speed of the skater was 18 meters per second, and the radius of the turn was 20 meters. We know that friction is our centripetal force because that's what's allowing the skater to go around in circles, and friction is what we're looking for. So any equation we have that talks about centripetal force is really talking about friction. So we solve for centripetal force, we've solved for friction. I'm going to use the mv squared over r equation because I have m, I have v, and I have r. Plugging my numbers in, I get 60 kilograms times 18 meters per second, don't forget the squared, divided by r, which is 20 meters. And when I plug in, I get a centripetal force of 972 newtons. And centripetal force is friction, so my friction needs to be 972 newtons. Now we're going to take a look at number 14. A 2 kilogram object is attached to a 1.5 meter long string and swung in a vertical circle. That's got a constant speed of 12 meters per second. What is the tension of the string when the object is at the bottom of the path? And what is the tension when the string is at the top of its path? This is one that, again, I really recommend drawing pictures for. So for part A, it's at the bottom of this circular path that it's on. And when it's at the bottom, gravity always pulls downward, but tension is going up towards the center of the circle. The mass is 2 kilograms, the radius is 1.5 meters, and the speed is 12 meters per second. My centripetal force is my force is going towards the center of the circle, which is tension, minus anything that pulls away, which is force of gravity. For my centripetal force equation, I'm going to pick mv squared over r because I have m, I have v, and I have r. Now I'm trying to figure out what the tension in the string is. That's the question. So I'm going to plug in t minus force of gravity where I had centripetal force because t minus force of gravity is the centripetal force. And I'm going to solve for tension. So I'm just going to add gravity to the other side. We did that in a problem just a couple ago. So force of gravity goes over to the other side, and I get mv squared over r plus force of gravity. I can plug in my numbers now. My tension is equal to 2 kilograms times 12 meters per second squared divided by 1.5 meters, and I'm going to add force of gravity, which is my mass, 2 kilograms times acceleration, or g, 9.8 meters per second squared. And that gives me a tension of 211.6 newtons is how much tension is on this string to keep this thing going around in a vertical circle. For part B, it's at the top of the path now. And when it's at the top of the path, the tension points towards the center, and gravity also points towards the center. They're working together. They're not working away from each other. So now I'm adding them up to be the centripetal force because they both go towards the center. So they're both positive. The equation I pick is the same. Centripetal force is mv squared over r. But now centripetal force is tension plus gravity, not tension minus gravity. So again, I'm going to solve for the tension. So I just subtract gravity to the other side this time. So it's minus force of gravity. And I get mv squared over r minus force of gravity. Plugging in my numbers, 2 kilograms times 12 meters per second. Don't forget to square it. Divided by the radius, 1.5 meters, minus mg, which is 2 kilograms times 9.8 meters per second squared. And I get a tension of 172.4 newtons.